not even start the main topic, but I want to talk about eigenvalues. I know a lot of you already know about eigenvalues. So we'll just start the topic, and this Thursday will be actually pretty fast because you would have come prepared with eigenvalues also and singular value decomposition also. So we would really run with all these ideas very, very quickly in the next class. But let's start. So this is the idea. This is the main idea, that I can decompose my matrix. You saw, right, that A is C into R, but that is not the only decomposition. There are actually even better and more special decompositions. Okay, and one of the decomposition is what is called as eigenvalues. Okay, what is an eigenvalue? So from the data science perspective and from the machine learning perspective, okay, again I'm repeating that because that's why we are here, is because we have a data matrix A, and that data matrix contains data from us. So data matrix is, let's say, m cross n, and we saw, right, that that data matrix spans some subspace. Okay, which means that it is part of a bigger subspace, but it is in a certain subspace, that column space, right? Now question is, even in that column space, are there regions where data belongs more than some other regions? That's the question. Okay, so if, for example, let's say, I'm just giving a little bit of an example here. Suppose this is my data matrix 1 0 5 1 4 0 3.5. Do you see what I'm coming to? Do you see what these data points, where these data points belong? All of them are actually sort of here, right, near the x-axis, right? Is
Yes.
that okay?
Yes, yes.
Okay, so the idea of eigenvectors is to determine those directions where the data actually has the maximum sort of energy. Okay, where the those dimensions or those directions, okay, those spaces where your data lies. Now one trivial space where all the data lies, this x and y axis, right? You can say that I can take x and y axis and actually put in all the data as combination of x and y axis. Of course you can do that because the dimension is 2. But are there better representation of the same data? Okay, and eigenvalues or eigenvectors actually exactly talk about that. They say that there are more intuitive, geometrically better representation of the same data that you have if you don't take the trivial canonical basis, right, which is 1 0 and 0 1. There are better bases to be formed, and there are better ways of putting the same data. And I'm little being ambiguous here, but eigenvalue decomposition is a step in the same direction. It's a step in the direction of finding where my data belongs. Okay, not exactly that, but we'll come to that later, right? What exactly it is, we'll come to it later, but this is the core of it, that you would like to find the eigen directions where your data belongs, and those directions may not be trivial canonical basis. Is this point clear? Yes, Shantika?
So, what is the meaning of maximum short of energy? I mean, the direction in which.
So just take this example, right? If I take these 5 data points, okay, this is 1 0, let's say this is 5 1, right? This is 4 0, this is 3.5. So these are my 4 data points. You see, if I just circle this area, all of them belong here, right? They don't belong randomly to R2. They don't belong to, they're not like separated like this. They're not randomly scattered across R2. They're actually contained in a very, very specific space in R2.
Okay, sir. Yeah.
So if I say that, if I have to take a direction, I'll take, this is one direction in which my data belongs, like this, right? Like this. So I'll take these two as my axis, and then if somebody tells me that give me just one direction, right, I'll give this direction. Okay, not some other direction, not this direction or this direction. I'll take this direction. That
That means I mean the close proximity is considered. I mean the points which are approximated together. I mean,
no. So again, right? Don't go there right now. I'm just giving you an intuition. Whether it's proximity, the notion of proximity, etc., will come to that probably when we look at such problems in machine learning. But right now, just assume that there are better representations, there are better basis. Better in the sense we will understand what they are better. What is the sense of being better? But they are better representation of the same data than canonical basis. You understand what a canonical basis is? Canonical basis is this 1001 in R2. In R3, it is this 1000 These are canonical bases. Okay. So obviously they can always represent any data, right? But are there better bases to represent data? That's the question we're asking. Okay.
okay, so yeah.
Or a different basis. Let's not even call it better right now. Different basis. Okay. So eigenvalues and eigenvector decomposition is basically eigenvector decomposition, as we call it, is towards that side. Okay. Now somebody will say that I know that eigenvector decomposition is only for a square matrix, and this is exactly what we will do when we do singular value decomposition. We'll convert a non-square matrix to a square matrix and then decompose that. But right now, let's say that I have a n cross n square matrix A. Okay. Then I'll say that there are some special vectors, right? Sorry, not X, such that when I take the linear combination of X, I mean, normally if I take linear combination of X, I get some vector Y, right? And that vector Y is not X, right? It's not in the direction of X, okay? But there are some special vectors X, which when I apply a linear operator A2, then I get the same vector except that in the scaled form. Okay, which means that when I take Ax, right, I get lambda x. That's exactly what I mean. You all know this. I know. I understand, right? But I'm saying that another way of looking at this operation, okay, Ax, is that I have a vector in certain direction, and I apply an operator A on that. Okay, operator A means basically taking some combination of x of the elements of x and resulting in some new vector y. Okay, now I'm calling it an operator. Okay, operator, for example, differentiation is also an operator. Okay, so when I apply an operator A on x, I do not get y a vector in a different direction. I actually get the same vector, but a scaled vector. Okay, vector in the same direction, but in the scaled form. Okay, and if that is the case, then x is called the eigenvector of A. Okay, of the matrix A. So when I apply an operator A on x, then I get lambda x. Then x is the eigenvector of the operator A. Okay. But why are they so important? I mean, we all know about it from, I think you must have studied EVD in like 5 or 6 courses for all I know, right? But why are they so important? Well, they are important for many ways, but here is the best way to look at it. Okay. What about A square? A into A, right? So you see, A square into X is basically A into AX, and AX is lambda X. Therefore, A into lambda into X is basically lambda times AX, which is lambda times X. Therefore, it leads to lambda square X, which means that this X is also an eigenvector of A square, right? So that is something that is not trivial, right? So basically, I have a vector X. When I multiply it with A, I get lambda X. When I multiply with A square, I get lambda square X. And similarly, when I multiply it with A to the power n, I get lambda to the power n. So this is, obviously it's a special vector, right? That I keep on multiplying with the same operator, and I'm not changing the direction of the vector. I'm still on the same direction, just that the scalar or the length of the vector is only changing. Right? Is that okay? Okay. Now question is, what about a to the power minus 1? What about a inverse? Well, A inverse is this, right? It's very easy to show. Of course, lambda should exist in this case. Lambda should not be equal to 0. Okay. So, okay. So this is the cool thing about eigenvectors, that the eigenvector of A and A square and A to the power n are all same. Just that their eigenvalues, the lambda, right, corresponding to the eigenvectors, they only change. And they also change in a very, very nice fashion. They are, they are just for A to the power k, the eigenvector is x and the eigenvalue is lambda to the power k. Okay. So that is the cool thing about eigenvector. Okay. Now, other cool thing, second most important thing about eigenvectors, that these eigenvectors are also the basis vectors. So if you recall, we had seen two bases now. We had seen column space, okay, and we have seen that column space can be represented by canonical basis. They can also be represented by the columns of A. Now I'm giving you a third basis, and that basis is nothing but the eigenvectors of A. Okay, so when they are bases, basically this is what I'm saying, that any vector in the column space of A, any vector in the column space of A can be written as the linear combination of eigenvectors. Okay, so two cool properties of eigenvectors. One is that they are eigenvector of A to the power k if they are eigenvectors of A, and that they form as the basis of column space of A. In fact, they also form the basis of column space of A to the power k, right? Same way. Which means that any vector V, okay, can be represented as the linear combination of the n eigenvectors or whatever. Even k eigenvectors. Any vector in the column space of A can be written as the linear combination of the eigenvectors of A. Okay? Because they are bases, we can write like this. All right? Is that okay? Is that okay?
Yes.
Okay, fine. So what I'll do is I'll stop here, and in the next class we'll continue with EVD, eigenvalue decomposition, and we'll take it to SVD, positive semi-definite matrices, and complete the linear algebra part that is required. Okay, and I'm again emphasizing that you guys have to go back and solve the questions yourself, but absolutely promise you that I'm going to send you questions by tomorrow. Okay, so you can also solve them. All right, so I guess that's for now. Yeah, Rohan.
So can you please share with me the classroom link? I think you did it in the last class, but I had left by then.
Okay, I will share with the classroom link with the course in the course email.
Okay, so actually today is the add drop date and I didn't register AOMML during pre-registration, so my name might not be in the course list.
Okay.